last year, and part of this year doing some synthetic organic chemistry, right? So first we have to talk about how to build stuff and why we want to build it, and then we'll talk about sort of how we go about doing that. So he's done a lot of fantastic work at all levels here in terms of understanding how this thing works at a fundamental level, all the way to sort of rolling up the sleeves and really getting in there. So please pepper him with questions, because he doesn't work hard enough and we need to keep poking at him. I'm just kidding. Jay is graduating, I guess technically graduating this spring, but already is employed. So he is a model for those of you students who hope to be in this issues shortly. And so if students have any questions about what it's like out there in the workforce, Jay can also, I guess, answer those questions. I'll see the floor.
Thank you, Stephen. Good to go on the video?
Go.
All right, so hello everybody, and welcome to my presentation in which we'll be discussing the exploration of open source synthetic routes to potential anti-malarials and other drugs. So we'll be discussing this one niche reaction, the Trifold Methylation reaction, and kind of talking about its reproducibility and its accessibility to us in school labs and other kinds of labs. So, but first I'd like to talk about the open source malaria project. The open source malaria project is an organization that it tries to deal with open source routes to potential anti-malarial drugs. Because one of the issues in pharmaceutical companies is that they make drugs and then they put a patent on it, and then so that they can jack up prices on these drugs, and that makes it very difficult when you're trying to treat a lot of people when it's so expensive. And so what the open source malaria project is trying to do is that it wants to find ways, it wants to put out the information out there for everybody to use instead of putting it behind a kind of a patent so that no one else can use it. So it very much cheapens these drugs for everybody to use. So malaria is the #1 killer in the world with over 1 million deaths per year. But we have often tried to come up with lots of drugs to treat this, and previous drugs worked pretty well, but resistance is always a problem, and has been for quite a while. So we're trying to find new drugs to kind of combat that problem. And so what we'd like to do is we'd like to create a whole bunch of analogs or drugs that that we can just test rapidly over and over as we cycle through a whole bunch of potential drugs. Because we can do that very fast, and we can find more potential drugs very fast. But I'd also like to emphasize we're not only concerned with anti-malarials, we'd like to talk about other kinds of drugs that we can potentially Trifold methylate or use. So our end game here is we need new molecules. If we create thousands of drugs, we're more likely to find better drugs. And but if we want to create thousands of potential drugs, then we need to come up with new methods that we can use to create these drugs. These old methods that we've been using in the past, they worked well at the time, but we'd like to do better because these conventional methods, they don't work very well. They're not very efficient. They just don't work very well. So again, to the topic at hand, Trifold methylation. Why do we want Trifold methylation? Why do we want a carbon with 3 fluorines to replace some other group like a hydrogen on some arene? Well, I'd like to emphasize that it's a very common motif in drug chemistry. It's very popular, so there's obviously a reason that we have it here. One of these CF3 groups can greatly change the properties of the entire drug molecule, which we'll discuss pretty shortly, and giving us lots of medicinal improvements into these drugs. So these CF3 groups, they change how these drugs can fit in the enzyme, and they also change how these drugs pass through a cell membrane, which then, in short, we can change also change the metabolism of the drug by the body, And because as the drug has to pass through the intestinal lining, the more nonpolar a drug is, it's easier to pass through the intestinal lining. And if the CF3 group, it slows down to break down, so then the body can break down the drug less easily through the liver. And so what this means is the end result is that we get easier dosing because of the greater bioavailability in the body, as it doesn't get broken down as easily. So what this means is if you want to, instead of having to take a drug every 6 hours, you can just take it every 24 hours. That's a lot easier to do that instead. So I'd like to talk about some drugs with CF3 groups. For our first one, we have methylquin, which is an anti-malarial. It's been used somewhat frequently. It's got two trifold methyl groups right here and here. The next one we have sorafenib. It's got it treats liver, kidney, and thyroid cancer. And we can see here it has this trifold methyl group here. And then we have halofantrin, which treats malaria as well. This is kind of a newer drug, one of the newer generations of drugs. We can see here we've got this trifold methyl group right here. So again, emphasizing this is a pretty common motif in drug chemistry. So, of course, this begs the question, how do we create a drug? Well, I've got, this is the target here, that we just kind of look at here, just an example. But I'd also like to point out that when we want to make a drug, we want to trifluoromethylates at the very beginning of, say, of this process. We don't want to trifluoromethylate at the end, because that could lead to trifluoromethylation in different places. We'd like for it to be very controlled, and so we can trifluoromethylate at the very beginning using a heteroarene, for example, chlorobenzene. And so if we can trifluoromethylate here, and then we can then think about how to attach that onto the rest of the drug. For example, this is the rest of that sorafenib. I kind of reversed around some mirrored. And then so we can then attach it onto the amine right here, and so we've got our completed drug structure here. So then, that's fine and all, but of course there's going to be obstacles that hold us back from trifluoromethylation. For example, carbon-carbon bonds are difficult to make. It's not trivial. And there's a reason we spend so much money every year trying to make carbon-carbon bonds, trying to find new ways to make carbon-carbon bonds. It's not a simple thing to do. And another thing about these conventional methods, they're difficult. These conditions are not ideal. We're talking, it's very toxic, unsafe reagents, or poor yields. We'd like to see if we can do better than that. It's also expensive. That's also another one of these obstacles here. We'd like to make it cheaper for all people to use. So let's talk about an older reaction called McLaughlin-Thoreau reaction. This is a reaction dating back to the 60s, I believe, in which we start out with iodobenzene right here, 1.4 equivalents of iodobenzene, and we'll be using a large stoichiometric amount of copper, 3.8 equivalents, and iodotrifluoromethyl. That is the trifluoromethylating reagent here in DMF. We'll be stirring that for about 12 hours at about 150 degrees Celsius. And then the end result is a trifluoromethylated benzene with about 45% yield. And that's not a great yield. We'd like to do better than that. So again, for theoretical, for yield. The iodotrifluoromethyl is it's very expensive. It's also a greenhouse gas. And it's gaseous, so this makes it kind of unwieldy to use in reactions. Because we'd like to just stick with regular solid or liquid reactions instead of having to deal with the gas. And it's also used at high temperature, so that's very energy inefficient. Very going to use lots of energy to get this reaction going. And this is not nearly as big of a problem as the rest of this, but we're using lots of copper. And if we're using lots of copper, it means it's cheap metal, but it can also be an environmental problem, having to deal with the disposal of all this copper. So this is a Minsky reaction, which does a little bit better than the McLaughlin or Morrell reaction. So we have pyridine right here, and then we have a terbutyl group here and silver nitrate. Now this terbutyl group here can have a trifold methyl on this terbutyl group, and we can have sulfuric acid and NH4S2O8 at about 70 degrees Celsius, and then we end up with this terbutyl group here attached on here. So what's nice about this is that there's no unwieldy gases that we would have to use in the previous reaction. No iodotrifoyl methyl to use. We have, the problem though is it consumes lots of silver, which makes this an expensive reaction to use. We're using at high temperatures, it's not going to be as high as the previous reaction. It's not going to be 150 degrees Celsius, but it's still going to be pretty hot. And we're also using concentrated sulfuric acid. So that's, we would like to step away from using harsh reagents. We'd like to step towards calmer, greener reactions. So what can we turn towards instead? Well, we'd like to use light to initiate reactions. Being that in these previous reactions we're using very hot conditions. And if we can bypass those hot conditions and use light to supply all the energy we need, then we can proceed forward with that. And then we'd also like to use catalytic metals. Because these catalytic metals, it's different from just using metal, because we can reuse this metal over and over and over. And so we don't have to worry about it being consumed as much as, say, silver nitrate. We'd like to use cheap, safe reagents, which I will be discussing in the coming reactions to come. And we could bypass these harsh conditions in these previous reactions, and we can jump to gentler, greener reactions, not using sulfuric acid. So let's talk about the first reaction, the McMillan procedure. So now this is a reaction that uses, again, any standard heteroarene or isocyanaridine using triplet. This is the trifold methylating agent right here, for 1,4 equivalents. And we're using ruthenium phenanthrolene dichloride at about 1 to 2% the amount of moles that we'd be using in the amount of moles of heteroarene. And then we'd be using K2HPO4 and acetonitrile at about 23 degrees Celsius. Again, that's room temperature, so that's quite nice. We're not doing 70 degrees Celsius or 150 degrees Celsius. And then, of course, we have to have our light source to initiate this reaction. So, again, catalytic usage. This is a photocatalytic reaction. We'll be using ruthenium phenanthrolene at about room temperature, light initiated. And it's considerably cheaper because, again, catalysis makes things cheaper usually. So let's talk about the photocatalytic mechanism. So we'll be starting out here with photocatalyst number 1. And this household light is going to change this into a reductant. And as a reductant, what this can do is that we can get a single electron transfer and dumping it to this triplet here into a bond of the chlorine. And then this CF3 group is going to break off, and it's going to become radicalized. And when it's radicalized, it's going to be able to attack the heteroarene right here at this specific hydrogen. And then it's going to push a radical onto this cation right here, onto this carbon right here. And then this oxidant is going to come around and take this radical electron right here. And then we get left with the carbocation right here, which is very unstable. And since it's so unstable, we're going to have to break the hydrogen bond to create a bond right here on this arene, and to get a more stable arene right here. So that's how we end up with that trifold methyl on this arene. But can we look away from metals? Because It would be also nice if we didn't have to use catalytic metals. What if we use a catalytic dye, which is methylene blue. So this here is the structure of methylene blue. And then what this is going to be doing is going to be reacting with Togney's reagent right here, which is the trifold methylating agent. And then you could react that with any arene and we'll give us a trifold methyl somewhere around here. So that would be about 30 to 79% yield, which, you know, again, we hope for the latter 79%, but not always going to be the case. So, safe conditions, it's not very harsh, it's not very difficult to use. We get somewhat decent yield, it's not great, but it's better. It's metal-free. That's an important part of this, this procedure. It's metal-free. But again, the drawback to this is Togney's reagent is expensive. It's going to be a very expensive amount. You have to buy large amounts. You want to use it to buy it and to react at a, say, gram or kilogram scale. So what this methylene blue, this mechanism of this methylene blue is it's very similar to the ruthenium milling procedure. Basically, this methylene blue is going to be kind of mapping onto in place of the ruthenium catalyst, and the Togney's reagent is going to be taking place of this triplet. So again, it's a very similar kind of procedure in this instance. Now, another reaction we'll also be looking at is an acetone diacetyl reaction, which we'll be using. This is acetone is standard nail polish remover. Diacetyl is the butter flavoring popcorn. So, what's nice about this reaction, it's very cheap. It's metal oxidant free. And we're using sodium SO2CF3, that's the trifold methylating agent right here. It's safe, relatively safe, I should say. Diacetyl has been known to cause popcorn lung, which is kind of a disease that will, it's like a permanent smoker's cough. So it's relatively free, but as long as we use it in a fume hood, it should be okay, somewhat okay. Yep, again, more environmentally friendly than these other previous reactions. And that's what I'd also like to point out that here we got to 95% yield and up to 93% yield. So let's talk about the mechanism of this reaction here. So what's going to happen is that we have our acetone or diacetyl. This R group can distinguish and the rest of the structure. So our light is going to cleave off this acetone or this group right here from the rest of the R group and get a radical over here. And this radical is going to attack the sulfur group right here. And it's going to attach right here. And then this trifold methyl group is going to break off into another radical right here. And then this radical can attack right here with this carbon with the hydrogen. And then this electron is going to get pushed right onto this carbon right here. Then what's going to happen is that we have this R group, the radical line is going to come in, and we have this other radical is going to push into a bond right here, and then it's going to push this off while this R group is going to take that hydrogen, and they're going to bond together. And then we get left with our trifold methyl group along with our RH group. So now on to the experiments. Our general methodology here is, well, all these reactions, they follow a very similar setup. The only reagents that are going to be changing across these reactions is, the reagents are only going to be changing across these reactions. So the general flow chart of this is that we're going to have a heteroarene along with other reagents. We're going to add that into a glass vessel, a round bottom glass, for instance. And then we're going to let it sit under a standard house light, so this can be any light bulb, for about 24 hours to a week, while this light is shining onto these reagents. And then we're going to run this crude reaction at the very end through a GCMS and see what we get. So I chose these heteroarenes, ethyl ester, nicotinate, and caffeine, because ethyl acid nicotinic is kind of a one of these heteroarenes that we'd like to look at maybe as potential substructure to a drug for the anti-malaria project. And I chose caffeine because caffeine tends to work fairly well in trifold methylating reactions. And because of that, we can set it as a standard, so we can compare the ethyl acid nicotinic reaction to this caffeine reaction. But of course, shortcuts will have to be taken. This is not necessarily a bad thing, not always, but this can affect our reactions. What these, for instance, in this case, these reactions, they call for replacing the reaction atmosphere with argon. But we don't have argon on hand, we don't have that kind of equipment, so we can maybe get away with this by using a freeze pump thaw. So this is going to likely affect our reaction success because of the oxygen in this reaction. So oxygen is a biradical, and so it interferes with the reaction. It kind of destroys the reaction because it wants to bind onto our radicals. So this is the same reason we want to take antioxidants to get rid of these free radicals in our body. So what we would like to do is we'd like to deoxygenate it. And one way to do this is a freeze pump thaw. So I'd also like to discuss one of these particular reactions. We had to use a special photoreactor and quartz tubing in the acetone reaction because we needed we needed about 300 nanometer light-ish, which is just enough energy to initiate the reaction. We want a quartz tubing because regular glass can cut off UV light, and so we like quartz tubing to allow that UV light to pass through, and we can use it to initiate the reaction. Okay, so we have here a freeze pump thaw cycle. This is a step in performing this right here in the picture. And we have our, it's kind of hard to see, but we have our little, it's a tiny little glass rod. It's got a reaction in here. And then what we're doing is that we're putting it into liquid nitrogen, and so we're freezing the liquid in the reaction vessel. And when we freeze it, then we're going to take that's what it's connected to a tubing here, and so we're going to take it and we're going to vacuum out the atmosphere, and then or the oxygen, and then we're going to let it melt. And then once it's melted, the oxygen is going to want to seek equilibrium, and it's going to progress back into the atmosphere. And then we're going to freeze it again, suck that oxygen out, and then let it melt, and then it's just going to keep continuing to do this over and over. And so until we have negligible oxygen in there. And so this is kind of a nice way to get around the whole argon backfilling thing. And I mean, at the end, you'll have to seal it off from the reaction atmosphere by kind of melting around the glass to kind of collapse on itself, and seal it off from the rest of the atmosphere, so it's not exposed. So that would be the freeze pump thaw cycle. So let's talk a little bit about the GCMS. So this is gas chromatography and mass spectrometry. What we have here is that we're going to be injecting our samples, and they flow through a long column. And the general scheme of this is going to be purification, a separation, and then to analysis, which is the MS part. So the GC part is the purification, and the MS is the analysis. And so, again, we're injecting our samples. They flow through a long column. And our crude compounds, they're going to get separated by polarity depending on the phase in this column as they're flying through this entire column right here. So then what's going to happen is going to fly into the line of fire of these electron beams. It's going to become ionized as it flies through. And then onto the MS part it goes. So then we have this quadrupole mass filter. So what this does is it shapes the magnetic field around the ionized molecule. And so this molecule of a certain mass and charge is it's manipulated in vacuum. And so what happens is as the ions are flying through this path right here, this mass spectrometer can select for one mass at a time. So it's going to be changing how this magnetic field is interacting with these molecules. And so we can select for one mass at a time and as it flies through. So, because any mass that is too large or too small to fit that will just fly into the wall and won't get collected by the ion collector. So then we can actually just go through a range of masses back and forth extremely fast. And so then we'll just measure and see what ions make it through. And then we can determine what we have. So here is an example of this, the ruthenium reaction with caffeine. What we have here is that we have two peaks right here. Now this is the second peak right here. This is at about 13.3 minutes, so it came off the GC at about 13.3 minutes. And this other peak right here came off at about 11.52 minutes. And so these two peaks mean two different things, two different structures. This first one right here is regular caffeine. And the second one right here is trifold methylated caffeine right here. And then we can look at this peak right here just to be sure that we actually do have trifold methylated caffeine. And we can look at it and we can see the different kinds of masses that we collected as the mass spectrometer was collecting ions. And then we can see here we have 262.1, which is the mass of the entire caffeine structure with the trifold methylated group on it. So let's, I'd like to talk a little bit about the GCMS peaks here. So we have caffeine has one place to trifold methylate, and therefore there's one peak to look for at about 11.52 minutes. So again, this is one place, the only place to trifold methylate. There's two trifold methylation paths for ethyl acid nicotinate, which is right here at the 2 position is about 7.35 minutes, and right here at the 3 position, which is about 7.0 minutes. And so we have also a starting material that we also need to look out for at about 7.5 minutes. And so we can determine between what we have, where our trifold methyl group might be, and if we got it at all. So again, these are our results. So this is the roof end result. We have 0% yield at the 2 position and the 3 position. Not exactly successful. But on the other hand, we did get 35% yield for caffeine, which is actually quite better than I was expecting. For a methylene blue reaction, they didn't work at all. We got 0% yield across the board. And for our acetone reaction, we didn't have enough time to set up for the ethyl acid nicotinate, but we get about 8% yield of caffeine, which is proof of concept. And then in our diacetyl reaction, we have 3% yield for the 2 position, and about 7% yield for the 3 position. And then we also we have caffeine with a yield of about 11%. Now, if we looked at the freeze pump thaw, we got about 25% yield, so that's more than double the other reactions. So that was quite nice. It was quite decent compared to the other reactions. So our roof end reaction was promising, except for the fact that it didn't work with ethyl acid nicotinate, but it had the best yield of any other reactions for caffeine. Our diacetyl reaction, it worked the best all around in terms of actually getting trifold methylated ethyl acid nicotinate and caffeine. But caffeine in general provided the best results, which was not surprising because we chose it as a standard. Ethyl acid nicotinate, maybe one of the reasons possibly that it wasn't working in some of these is that maybe the ester gets cleaved by light. So maybe that was one of the reasons we didn't get any yield. There were also some complete duds, like the roof end reaction and the methylene blue reaction. Something may have gone wrong is that oxygen is, again, likely the largest source of failure here. And maybe our reactants were just a bust. Maybe the methylene blue was just didn't was too degraded, or some of the other reagents just didn't work at all. So going forward, what this means for us is that these reactions, although not as successful as we would like them to be, can be more accessible to labs that don't have access to the same kind of equipment, such as argon backfilling, and so it's more accessible to these people. We can also explore, perhaps in the future, new, more heteroarenes, expanding outside of ethyl isonicotinate. And maybe we can also look at new Trifold Methylation methods. For example, there's iridium. Iridium catalysts. Now they behave very similarly to the ruthenium catalysts, but these iridium catalysts, maybe they could work better in some instances or not. That's just one thing to test. We'd have to find out. And then we'd also have to consider looking to the freeze pump thaw cycle more. We didn't have the time to do freeze pump thaw for every single reaction, but it was clear that it really did have a more profound impact on the success of the reaction. And again, maybe we can get some of this equipment to do some of this argon backfilling, some argon to do this sort of stuff. Maybe that would be very helpful for us in the future. And maybe we'd also like to look outside of heteroarenes. Maybe we'd like to do certain trifold methylation reactions for things that aren't heteroarenes, and then consider implanting that onto different kinds of drugs, drug structures, like alkynes or alkenes or so forth. I'd like to thank Stefan for helping me with this entire project the most. He gave me a lot of guidance and a lot of tips and taught me a lot. I'd also like to thank Dave for helping me a lot with this presentation as well, and DMART, of course, for providing all the help with the stock room and all the equipment and chemicals, and of course to Graham Sazmar for helping me out a little bit too with this presentation. So thank you guys. And you guys have any questions? Yes.
Why not nitrogen for backfilling?
What?
Why not nitrogen for backfilling?
What did you say?
Why not nitrogen instead of argon?
Mm-hmm.
Is there a difference between nitrogen and argon for backfill?
I mean, argon would be a lot less reactive than nitrogen, but I think one of the issues is we didn't really have that kind of equipment to just kind of place nitrogen into the atmosphere, did we?
Yeah, I mean, it's pretty much a horse apiece. We can do that, but the freeze pump thaw is actually quite a bit more, should be a lot better than just backfilling.
Yeah, that's true.
So you suggested that you thought that the ethyl isonicotinate, I'm going to say it wrong, whatever, the nicotine one, that it was light sensitive. How do you know that's a light sensitivity versus just being more sensitive to if there's any oxygen in the atmosphere? Because that, how did you separate those two, or is it still mixed together?
I'm separated two from just temperature, oxygen sensitive and just light sensitive, you mean?
Yeah, you would give a suggestion about that. You thought maybe it didn't work as well because it had extra light sensitivity. How do you know it's not just more oxygen sensitive?
We don't know if it's not just more just because of the oxygen either, but I do know that Stefan had also speculated that maybe light can cleave the ester of this ethyl isonicotinate. But yeah, I'm not sure. What's up?
What sorts of side products would result from light cleavage of the ester? What sorts of side products would you expect if light had in fact cleaved the ester, and did you test for them?
No, we didn't test for cleaving these.
You want to try? What do you think would happen? What could happen to the ester?
If it cleave the ester?
Yeah.
Try.